Good night, my name is Diego Paipilla, and with my partner Andres Moreno, we're going to talk about the HVDC technology. We're going to talk about the paper New HVDC Technology in Pan-European Power System Planning, and the authors are below. First, we're going to talk about DC-DC converters, then an introduction to HVDC. After that, environmental benefits and drawbacks, and finally, we're going to talk about HVDC projects.
Okay, first, the DC-DC converters. The DC converter are widely used for the traction motor control in electric automobiles, trolley cars, marine hoist, forklift trucks, and main haulers. They provide smooth acceleration control, high efficiency, and fast dynamic response. But in the input and output voltage of a DC-DC converter are DC. This type of converter can produce a fixed or variable the output voltage from a fixed or variable DC voltage and show in the figure in left. The output the output of voltage and the input current should ideally be a pure DC, but the input voltage and the input current for a practical DC-DC converter contain harmonics or ripples as shown in the figures in right. The converter draw current from the DC source only when the converter connects the loads to the supply source and the input current is discontinuous. Okay, the step-down converter, when switch SW known as the shopper, is closed for a time T when the input voltage Vs appears across the load. If the switch remains off for a time T2, the voltage across the load is zero. The waveform for the output voltage and load current are also shown in the figure in right.
We also have a simulation so that it can be easier to see this step down converter. So we're gonna start the simulation. So when the switch is closed, we see that the output voltage is direct, and when we open, it goes to zero. And the output voltage of this converter, it's gonna depend on the time that we leave the switch closed or open. Now we're gonna make an introduction to HVDC. So we're gonna start that the meeting the energy and climate policy targets set by the European Union for 2030 and beyond will pose several challenges towards the development of the European power system. Concerning the European transmission grid, the critical goal will consist in the optimal network integration of massive amount of electricity production from variable renewable energy sources. In this context, among various potential measures and available technologies, a key role may be played by advanced high voltage direct current or HVDC transmission devices. Because of their features, this technology are already widely used and preferred over HVAC for selected applications.
Furthermore, HVDC assets might provide the system with environment benefits with respect to conventional HVAC transmission technologies. The ongoing progress and fast developments in power electronics on top of the traditional characteristics of HVDC may impact to further extent the topologies of HVDC application in the European system. This trend makes HVDC emerge as boosting technology in a mid to long term horizon in Europe. This concerns especially to most advanced self-commutated VSC or voltage source converter HVDC system due to their characteristics. In parallel, also classic line commutated CSC or current source converter HVDC technologies are expected to be further applied in Europe.
Now we're going to talk about environmental benefits and drawbacks of HVDC converters. In this regard, HVDC technology has raised concerns about the effects of the resulting electromagnetic fields on the environment, including the impact on human and animal life. There was a study that was carried due to this concern about an underground HVDC line that was laid for power transmission between England and Ireland. The resulting report states that the magnetic field at 1 meter from an HVDC line is not stronger than the Earth's magnetic field, which is approximately 50 microteslas. Another possible direct impact is presented by the electric field or by charged air ions, which in turn are a product of the electric field. The various effects of the electric field observed by humans near HVAC lines are greatly minimized compared to HVDC lines. There's also a concern about another possible environmental impact by HVDC transmission is electromagnetic interference with the radio frequencies. Such interference is related to the corona, which is an electric discharge due to air ionization around a conductor. Such corona effect exists for HVAC AVAC lines as well, and it's generally of higher amplitude, in particular in case of rain or wet weather conditions or high temperature. Finally, another potential problem is with the marine HVDC cables, and there are three reasons why. The first one is the impact of electrolysis products on marine organisms. The second one is the impact of electric field, which can be sensed by some sea creatures. And finally, the effect of the magnetic field in the fauna habits.
Okay. In the other hand, the converter station for an HVDC network requires a larger area than for HVAC. A converter station for 100 megawatts power line at a voltage rating of 400 kilovolts would require a plot of a length of 3,020 meters by 270 meters, which is considerably lower than for an AC substation. Okay. And now we will talk about projects with HVDC. For relatively long time after the reintroduction of direct current transmission in and 1954, the use of HVDC transmission has been restricted due to technical reasons to interconnection of non-synchronous networks. Submarine cables starting for the Gotland subsea link in 1974. In the following years, the substantial increase. In the following years, the substantial increase of HVDC voltage and power rating subsequently put HVDC power transmission on a par with HVAC. From the beginning, long-distance overhead DC lines were built, such as the Pacific DC Inter-the Cabora-Bassa interconnection and the Nelson River projects, culminating in the Itaipu system in 1984 to 1988, which each bipolar linked rated in 3,150 megawatts. And the Itapu voltage and power records had been now broken for 20 years.
Now, in the first decade of the 21st century, there was a rise in the HVDC transmission projects characterized by three major trends. The first one is the new submarine HVDC links in Europe, both in the North Sea and in the Mediterranean area. Also, the construction of a large number of long HVDC lines in China to provide support to the steep growth of Chinese demand. And China was building the first ever HVDC lines at 800 kilovolts DC and with lengths sometimes in excess of some hundreds of kilometers. And finally, the introduction of a completely new technology in HVDC converters consisting of several VSC topologies characterized by the use of IGBTs switches. Now we're going to talk about the future projects in HVDC. In the figure, we can see the evolution of the new net transfer capacity, or NTC, which is expected to be installed by 2030 over the TY-NDP-18 perimeter. It can be seen how the expected total increase in the new NTC is almost 10 times the new capacity installed in 2019. The greatest contribution to this increment is given by HVDC projects planned as a reinforcement or replacement of the European grid. Nonetheless, the new NTC associated to offshore plants represents a non-negligible part of the total at 2030. With respect to the numbers of projects planned, a total of 52 HVDC lines are expected to be commissioned by 2030 for a total over of 25,000 kilometers of new HVDC lines versus 300,000 kilometers of HVAC lines.
Okay, in the figure in left represent the country involved into HVDC projects, highlighted in dark, whereas in the right figure summarizes the number of projects or for each country considered in the TY-NDP parameter, divide and both HVAC and HVDC, taking into account only project under construction. The HVDC system will grow of about 3,100 kilometers progressively and in 2019 to 2012 one. It can be seen how Germany leads in terms of number of projects for AC lines, and it is also the second country in terms of DC lines. Other noticeable countries in this rank are Spain, the Netherlands, and Belgium. UK is the first country for number of new HVDC projects, followed by Germany and Italy. Sí, eso me toca a mí, sí. In Italy, there are the about 100, pardon, 1,166 kilometers of direct current power lines, mostly submarine cables. The total installed capacity is 1.8 gigawatts. In the left figure shows the installed Italian HVDC systems. All of them are based in CSC technology. And the first Italian HVDC is the SACO 1 between Sardinia, Corsica, and the Italian mainland. It was commissioned in 1966 to export from Sardinia to the mainland the hydro and thermal power production, which, which was higher than the island's load.
Now, in the right figure, we can see that in the Italian National Development Plan, or the NDP, the new connection SACO I3 has been planned, which will replace the old SACO I2, and it will assure adequacy margins of the Sardinian electric system. And this figure also shows all the future HVDC plants in the NDP, in the Italian National Development Plan, with the different phases of progress. All of them are also included in the TY NDP 18 and have been evaluated through the process and have been evaluated. In addition to the RES integration and the improvement of the system's flexibility, the use of HVDC technology can also increase the exchange capacity between congested zones and with the foreign countries, guaranteeing the integration of European markets in the energy transmission. That's all. Thank you for your attention. Good night.